Yeah, so I'm Annelies Mortier, and after this brilliant talk by Heather, my job just got easier. So I'm going to tell you about what we can actually learn if we want to treat the sun as a star. I know the sun is a star, but it's not that straightforward sometimes. So just to remind you what we're talking about, here you see the total number of planets discovered in a logarithmic scale versus the year that they were discovered. And as you can see, it linearly goes up, which means that we exponentially discover more exoplanets over time, although in the last couple of years we seem to have slowed down a little. So the doubling time is about 29 months, so that's lots and lots of exoplanets that we find. And if you plot those, I think Deborah Fisher showed this plot as well, in semi-amplitude versus the year of discovery, you see that we are pushing down in semi-amplitude, and that is mostly because instruments were getting better. But from the early, middle 2010, it seems to have flattened out. There's only two planetary systems that broke the 1 meter per second barrier, and they have respectively 5,000 and 8,000 radial velocity points. So that is the main reason that they managed to do that. Instruments, as you've heard the other day, are really getting better. We can break that 1 meter per second barrier for instruments. The people building those, I just have so much respect for them. It's just really the stellar activity right now that we're struggling with. So it's my favorite motto, and if you take one thing away, you can only know your exoplanet if you know your host star, and that is not just because we do an indirect measurement. It's about much more than that. And, the most problematic noise, between quotes, in radial velocity data is actually not noise. The most problematic signal that you see in radial velocity data is, as Heather explained, the star itself just being a star on a daily basis. This is a beautiful picture of our sun throughout the magnetic cycle, where you can see it going from solar minimum to solar maximum back into solar minimum. And if you haven't yet watched the 1 hour long video that NASA recently released of the sun in detail over time, you should. It's just wonderful to just sit there and watch the sun being the sun. So all this activity happens on the sun, so we can be quite sure that they happen on other stars as well. And they will obviously affect our data. So if you will ever want to find an Earth twin, it's crucial that we understand the kind of effect it has on our data. But the good thing about being able to do this with the sun, the fact that we can make these detailed pictures of the sun and actually see what's going on, actually see these spots, see these faculae, see these beautiful convection cells, see the flares, see everything. If we then treat the sun as a star, the biggest benefit of that is that the sun is the only star that we know 100% sure has no orbiting planets, because you can remove them from the data. There is not a single star in the entire universe that we can be 100% sure that is the case. So if you treat the sun as a star, remove the effect of the planets in the solar system, then you're basically left with a data set where everything you see is either instrumental or stellar. And you know that for sure. So that is the biggest benefit why we are observing the sun as a star, to learn more about this. So these are the kind of things you can do. If you want to have details of all of those, I recommend you watch the pre-recorded talk on YouTube, which is, I apologize, over an hour long, but it has many more details about these types of work. So one thing you can do is simulations. Use either simulated spectra, simulated cross-correlation functions, simulated radial velocities directly. And then from these simulations, the good thing is that you know the types of physics that goes in, and then see the effect that it presumably has on the data. But then you can also take actual data, and you can either do that indirectly or directly. Indirectly by, for example, reconstructing from these resolved observations, these beautiful observations where you see the sun in detail, and then blur it all together so that you treat it as a star where it's just one averaged measurement. or indirectly by using our exoplanet spectrographs and bouncing the light off via the moon or via asteroids. That has been done a couple times before. But recently, for the last 5 years, I've been doing this directly. It's not the first time that the sun is being observed directly with high resolution spectroscopy, far from it, but it is the first time that the sun is being observed in high resolution spectroscopy that is specifically designed to be stable over a long period of time. It's the first time that it's been done with a type of instrument that guarantees not just the very low precision, but guarantees the stability over time, which is the crucial thing we need when you look for exoplanets. So both HARPS North and HARPS South have a working solar telescope attached to the spectrograph, and there's several more coming. As far as I've heard, almost every high resolution spectrograph that is planned will have some sort of solar data attached to it, which is awesome. So for a little bit more detail, so one of the results of the simulations, for example, was what Heather talked about, that the suppression of convective blue shift is the main source of solar RV variation. I think it's important to say that this is about solar type stars, obviously, because we're observing the sun, so this is just relating to solar type stars. If you go hotter or cooler, the main variation is the suppression of convective blue shift. In the top row, you see the radial velocities from her simulations from Mortier et al., where this is just, the y-axis is just the radial velocity from the convective blue shift. It's in meters per second, and you can see that it goes from 0 to 10. It's over the length of an entire magnetic cycle, where the low part is obviously the solar minimum, and you go higher up and then low again. As you can see within that cycle, there's lots of scatter inside of it. If we zoom in on a lower activity period in the middle and a higher activity period at the end, you can clearly see this periodic pattern where the period is related to the solar rotation period. The same was done for spots and plages, where the effect, when it's in a higher activity region, the effect can go up to a couple meters per second, just as with faculae. During low activity periods, the effect of spots sometimes is completely gone, because sometimes, if you've been looking at the sun lately, sometimes there really are no spots on the sun. There still are faculae, but they have a minor effect. So if you combine all three, the faculae, the spots, and the convective blue shift, the shape still looks the same as the convective blue shift one, because it is the main source of this variation. So indirectly, this has been confirmed very recently by reconstructing radial velocities from the detailed resolved SDO observations, where in the top you see a full magnetic cycle again, but it's one later than the one that I showed you before. And you can see again that over the time of the magnetic cycle, we go up and down, and the scatter can be quite large. The scale here goes from 0 until 18 meters per second. During solar minimum, it's quite low, but it's still a couple meters per second. Now, the other thing this study from Raphael Hewitt showed is that the magnetic field, the unsigned magnetic flux density, actually tracks these radial velocity variations quite well. So because we have the SDO mission in the resolved observations, they actually do have a measurement of the magnetic field of every pixel of the sun, which you can then combine to have the averaged unsigned magnetic flux density of the sun at any point in time. And as you can see just by eye, it correlates really well. If you just use a linear model, a simple linear fit, which I would never recommend you ever do for a published paper, but if you do a simple linear fit with the magnetic field, then you can actually reduce the scatter of the solar radial velocity variations by 62%. That's a factor of 2.6, and it's quite impressive. No other activity indicator has yet been found that does a better job. The problem is that getting that magnetic field measurement simultaneous with our radio velocity measurement from the spectra that we take is currently not really possible. It is something that my PhD student Florian Linhart is working on, so if you want to chat with him about it, I encourage you to do so. Now let's talk about the direct observations then. So this is the solar telescope. On the left is the solar telescope that feeds into HARPS-N. On the right is the TNG, which is the main telescope that we observe the stars. So during the night, HARPS-N works on the stars. During the day, it works on the sun. It never stops working. It never gets tired. It's fine. Now, if we zoom in a little, then you can appreciate the scale of our teeny tiny solar telescope. It has its own little dome platform next to the dome, and you can, it has its own little cover bubble, and it just sits there happily on its platform, observing every day. We've been operational since July 2015. And we take daily 5-minute exposures starting from 9 a.m. automatically until about 4 p.m. It really depends on the observer when they need to start get ready for the night. So that's a lot of data. Then since 2 years, since October 2018, and there's now HELIOS, that is the solar telescope that feeds into HARPS. HARPS and HARPS-N are very similar spectrographs. One is in the south, one is in the north. So it also has its own little platform. It also has its own little dome. This one opens up. But there's also been doing daily 5-minute exposures that they do with HELIOS. Now, why 5-minute exposures? Well, if you paid attention to Heather Segla's talk, then you should know why we take 5-minute exposures. What I show here is a day of testing that we did where we didn't do 5-minute exposures, but we did way shorter exposures. So this is over the course of 175 minutes. That's about 3 hours worth of data in meters per second, going roughly peak to peak from -2 to 2 meters per second. And you can see that there's a lot of scatter that happens on minute timescales. So these are the oscillations that you see. If we bin this data down to 5-minute exposures, which is the red curve that you can see now, you can see that the scatter is greatly reduced. The black points originally had a scatter of almost 1 meter per second, whilst the red points is about 48 centimeters per second, which is not far off of our internal error. So these 5-minute exposures that we do on the sun, and which we actually also do on stars, or even longer on stars, they average over the oscillation variations, and it's just one type of stellar activity you can then start worrying less about because the averaging, because of your longer exposure time, does quite a good job for this. So I recommend these 2 papers if you want to know more about it. And the last paper also has a tool connected with it that for a specific type of star, you can actually judge what the best exposure time should be to average out, because these oscillation time scales do change with spectral type. All right, sun as a star. I've said this 100 times, but is it just another star? When we started observing, we noticed that there's a daily downwards trend. So if you take the data over a day, this is all our data, just face folded with a day, that there was a trend. The red line is a fit of that data. There's a downwards trend in every single day, which obviously first we didn't really know how to explain, but it is due to the fact that treating the sun as a star is not that straightforward. The sun, unlike stars, are actually resolved in the sky. It's an actual circle that you see, and it's not a dot. The effect of that is that whilst it's rotating on an angle, and moving through the sky, the blue shifted and red shifted part of the hemisphere will be differently extinct by our atmosphere. This is not an issue you can have with stars, because stars are dots as far as our atmosphere is concerned. The sun is not. Luckily, we do know the angle with which it rotates. We do know the position of our sun all quite well. So it's an effect that we can analytically calculate and then take out. And once we've done that, the fit is flat and there's no more daily downward trend in the data. So again, it's not something to worry about with stars, but it's something to worry about if you really want to treat the sun as a star. Okay, let's look at the data. So HARPS-N now has 5 full years of data, minus a gap where there was a problem with the telescope, with the fibers. And what you see here in black is that data in radial velocity meters per second versus time. And what you see in blue is the effect that the Earth has on the sun. So it's basically the signal you would be looking for if you would be looking for a true Earth twin around a solar type star with radial velocities. So basically what all of us are trying to do is to find the blue wiggle in the black mess. And it is a mess. Can I just remind all of you that the first 3 years of radial velocity are already public. The first 3 years of spectra and cross-correlation functions will be released on the 1st of September 2020 through DAYS, which you now all know. Now I have the honor to show you our newly reduced data. The attentive listener from the pre-recorded talk of people who heard me before know we had an issue with daily calibration jumps of about a meter per second or less. These have now been taken out, but the other thing that it showed is that the data now looks like this. Now I can't see your faces, but I imagine that there's shock on quite a few of your faces. It seems like we just made it worse with the new reduction, but I can assure you we didn't. The trend, this is now visible, so the trend that we actually had in the previous reduction was due to the aging of our calibration lamp. Because we no longer do daily calibrations, that was taken out by a freak coincidence. The trend that was taken out coincided with the trend of the magnetic cycle of the sun. Because this is what you see here, the fact that the trend goes down is the sun going into solar minimum. That if we look at the calcium index, the log R prime HK, you see the same thing. It goes into solar minimum. If you want to know what RHK is, Jen will surely tell you in the next talk. So although it looks like we just made it worse with our new reduction, we really didn't. And this is a much better reduction. The jumps in between days have actually been reduced quite well. We know that for sure because we have both HARPS-N and HELIOS, and Chile and La Palma overlap with a couple hours. So we do have data overlapping of the HARPS-N Solar Telescope and the HARPS-South Solar Telescope. So which you can see here, the blue HARPS-N, the orange HARPS-South, and some of the more crazy variations that sometimes we thought, well, okay, this must be instrumental or a cloud, are tracked in both data sets that are nowhere near one another. The difference between each other is 43 centimeters per second, which is the error on both instruments. So it's quite precisely that we know for sure we're doing a good job here. And this is really the sun being the sun on a daily basis. Now, does the data contain this solar rotational signal? That is the question. And yes, it does. Here you see a periodogram. It is flipped. It's multiple periodograms. So you learned about periodograms yesterday. On the y-axis, we have time, not power. And on the x-axis, we have period, and the color is the power, well, probability in this case. So the darker the color, the more probable a periodicity is. So as you can see, the solar rotation, which is about 27 days, or 28, clearly shows up in the data. There's no denying that. But what you can also see is that it wiggles a little. It really depends. Sometimes the data picks out 25, sometimes it picks 32, sometimes 27. It's very unstable over the course of our observations. It also shows the 13 days, which is the harmonic. It's half of the rotation period that also shows up, not in this picture, but at 9 days, which would be 1/3, we do see signals as well now. And, so the solar rotation very obviously shows up in our data. In case we weren't sure yet that the variations we saw were actually stellar, I think this is plain confirmation that they are actually stellar. There is no hidden planet that would make this signal in the solar system. Now, so what about our activity indicators? I know Jen will talk about what they are and how we measure them, but just as a quick glance of what we found for the sun is, for example, you do expect correlations because we call them activity indicators for a reason, right? So you see here the full width of half max. This is the width of our cross-correlation functions that we use to measure the radial velocities versus the radial velocity. And we would expect a fairly linear correlation because both the full width half max and the radial velocity show a very similar periodic structure. If you make a periodogram, for example, they both show 27 days, they both show 13 days, they both even show the 9 days. So it was sort of a wonderment why the correlation seemed a little blurred out, and you can see a hint of it being linear, but really it's nothing more than this little hint. We found that this is because there's actually a time lag in the time series. So if you have a radial velocity time series or full width of half maximum or a bisector, which Heather just talked about, they are correlated, but they're correlated shifted with 2 to 3 days. And because you have that temporal offset between the series, if you would just look at a linear correlation, your correlation will be obviously weakened. And it's immediately the reason that I told you before not to use plain simple linear fits, because the simple linear fit will be blurred out and you run the risk of actually introducing signals in your data. The correlation, so this is a student of mine, James Hazard, who used 4.5 years of HARPS-N solar data, split it in chunks of 55 and checked the correlation coefficient, corrected for that time shift over time. So as we know, the sun was going into solar minimum over our data span, and you can actually track that in how well it correlates. In the beginning, so these are just 4 different correlation, 4 different activity indicators. So this one, top left, is the bisector, for example, which in the beginning correlated quite well with correlation coefficients between 0.6, 0.8. And then by the end of the data set, the correlation was gone. There's, when the sun is in solar minimum, most of these effects that you see here that show maybe a hint of correlation, it's a mathematical fluke in most cases because we visually checked. At the end of the data, where we're now in solar minimum, the correlation with most of our typical activity indicators is actually gone, and that's not good news because the radial velocities still go all over the place. What about photometry? I've seen this question before. Can we track this in photometry? And the answer is yes. You can track it in photometry somewhat, but it's not that straightforward. One of the reasons for that is that faculae, which is currently the dominant source of this suppression of convective blue shift, because we barely have spots, the faculae don't really show up in optical photometry. They're much better in UV photometry, but there's not a lot of that around. So it really depends on the type of photometry you have and the type of model you use. This is work from Molly Kosiarek that she recently did with Ian Crossfield, and there's also Shani Nava with a recent work. So these are periodograms of the HARPS-N solar data in purple, the HARPS-N full width at half max, I think her label's wrong, in pink, the bisector in orange, and then 2 sources of photometry in blue and in green, just to track. And the gray is where you would expect rotation signals or other related signals and harmonics to show up. And you see that sometimes it sort of works, but quite often it doesn't. Where the HARPS-N solar radial velocities are sometimes flat, the photometry peaks, and the other way around, where it peaks, the photometry does not. So while it can track it, it's really not that straightforward to directly track it. They did try to use Gaussian processes on the photometry, which is then relayed on the radial velocities. It's been a technique that's been used for stars as well, to use both to control the hyperparameters of your Gaussian process, which Vinesh told you about yesterday. It sort of works, but you really want to have simultaneous photometry if you do that, because obviously stellar activity does change over time. So lessons learned from Sun as a Star, that's the title the SOC gave me. Well, there's loads of lessons that we can learn from treating the Sun as a star. There's several on here that I haven't even mentioned, but I urge you to look at the pre-recorded talk that has many more results. And yeah, see, time is up. That's it. Thank you.
Yeah, thank you very much. Very nice talk. There are a number of questions in the Q&A. The first one is a more technical question or about understanding your graphs. And it asks why there is a peak once the full period is reached.
There's a peak once the full period is reached. On which graph?
I guess this must refer to correlation functions.
Sorry, I don't know what your question means.
Okay, I think this is about the interpretation of correlation functions where you see peaks. But
the question mentions a power peak. I don't know if that helps.
Oh, well, this is the only place where I have a power peak. No. So I'm not quite sure what you mean with the question. If you can specify later, I'm happy to answer it. But I just, sorry, that you're going to.
Yeah, so I guess perhaps the answer may be related to the fact that after a full period, you see the same phase of the Sun again. And then there's a higher correlation than at other times, right?
Oh yeah, well, so if you have activity regions on the surface of your, let's just take one spot, because the Sun rotates, it's going to rotate in and out of view, and because it rotates with the solar rotation period, there will be a solar rotation signal happening just because that spot moves from the blue shifted part to the red shifted part. From the blue shifted part to the red shifted part of the Sun, it'll block light differently. So whilst it's moving with a period of solar rotation period, your radial velocity will get more red shifted and then more blue shifted, creating that 27-day signal, which is not stable because there isn't such a thing as just the one spot. There's multiple spots, and spots disappear and appear again, which is why the solar rotation period is only partly measured. And it's also why we have the harmonic, because you only see one side of the Sun, right? So you only see half of the rotation period in one go.
Mm-hmm. Yeah, then there are a number of questions about the temporal offset between radial velocity and stellar activity. First of all, what does that really mean?
That's a good question.
Do we understand the reasons for that?
We only partly understand how it happens, what it creates. We do know that we have seen it in stars. So there have been stellar papers where we observed a star with high enough cadence that we could, and a big enough activity signal that we did see the shift with a couple days. In that case, it was also, I think it was 2 days also in that case, where we clearly saw it in stars. It is partly physical, partly related to the way we actually measure these activity indicators and the radial velocity, but it's partly also physical with limb effects, mainly going on the limb and off the limb, but it's not terribly well understood at the moment. We are looking into it. So one question I've had before is whether this time lag stays stable over time. And that's one of the things that James Hazard also looked at. Then in all the seasons where we actually did have some form of correlation between the radial velocity and our indicators, this time shift did stay stable at the same time. It's not that it shifts around from 0 days to 5 days. It was always quite consistently 2 days. Why? You're happy to all work on this. The effect it will have is that it blurs out correlations, and it makes using linear fits in your model with activity indicators very tricky, because they're clearly not linearly correlated. They're very correlated, but not linearly.
Yeah. Then there is a question regarding the intriguing correlation between the solar magnetic field and the RV variability. So one question regarding that is that stronger on a per pixel basis compared with the disk average? And the other question, how does it vary depending on wavelength?
I can't remember whether we looked at per pixel. This is averaged. So averaged, it clearly works. It has been shown as well with indirect observations bounced off of the sun. And we do plan to look into it with our HARPS and our solar data as well. What happens with it. The only thing I can say for sure is that the correlation is the strongest correlation that we thus far have found between an indicator and a radial velocity measurement. The problem really is that you would need that simultaneous. Things like fluid half max bisector, these come sort of for free with the spectrum and the cross correlation function that you do. Getting magnetic field values, precise magnetic field values for stars from integrated spectra, intensity spectra, is just not that straightforward. So, but we're working on that, because clearly it seems to be a very good correlation, but we haven't looked at what the effect is per pixel. Yeah.
And so one final question, since we are talking a lot about magnetic fields and their effects, does the Zeeman effect also play a role?
Presumably yes, because the Zeeman effect, for people who don't know, is where your line actually splits in multiple lines because of the magnetic field. The Zeeman effect is dependent on the type of spectral line, for starters. It has a different effect in every single line, and it's also dependent on the wavelength. So it has a larger effect if you go towards the red and the infrared than it does in the blue. So the Zeeman effect can play a role if active regions, these magnetic regions, because they move on the sun, they will affect the line on the red part or the blue part, depending on where the magnetic region is. It will be differently split. It will be differently split for every single spectral line. So it can have an effect. It's something that Florian is using in the methods that he's developing. But I warn you, this effect is tiny. It's really, really small. So you can't just see that in one spectral line. You still need, just as we do for the radial velocities, you still need the information of thousands of lines combined in order to give us the precision that we need, obviously.